Good morning, guys. I hope you're doing well. So today we'll look at graphs of logarithmic functions, and you'll find that a lot of ideas or things that we do with these graphs are the same as the things that happen with exponential graphs, with polynomial graphs, with linear graphs. The transformations and translations are most of the time going to be the same. Now we'll start by identifying that that an exponential function 2 to the power x is the inverse of a logarithmic function with a base of 2. And that is proven because when you graph these two functions, they appear to be reflected over the line y is equal to x. And we talked about how if two graphs are reflected over the line y is equal to x, that means that they are inverses of each other. So if the input value for this function is 2, the output value is going to be 1. That means that if the input value for the other function is 1, its output value is going to be 2. I hope that makes sense. The input value for the logarithmic function is 2, so therefore its output value is 1. So it's a 0.21. The exponential function will be the opposite. For an input of 1, for the exponential function over here, its output will be 2. So since you see that they're flipped, then they're inverses of each other. A logarithmic function is the inverse of an exponential function. Some characteristics of the graphs of f of x is equal to log of x to the base b. For any real number x and a constant b greater than 0, where b is not equal to 1, this b cannot be equal to 1, we can see that the following characteristics of the graph. 1, the graph is a 1-to-1 function, meaning one input to one output. Another characteristic is that the vertical asymptote is always going to be equal to 0 if that function looks like this, right? If there are any changes to what's inside this parenthesis, if maybe there's a plus or minus something, then that might change the vertical asymptote, and then I'll show you how to get that if that changes. The domain, as you can see, this being a vertical asymptote, this graph will never touch that line. So the line x is equal to 0 is going to be at the beginning of my domain, but except that it's not included. So my domain will be from 0 to infinity. The range will be negative infinity to infinity because this continues downwards and it also continues upwards. So the range is negative infinity to infinity. Now there's some key points you need to sketch this graph, one of them being the x-intercept and the other one being the x value, which we're calling b, the x value where the y value is equal to 1, right? So for each of these graphs, one, find the x-intercept, and that's the x value where the y value is 0, because this is x and y. That's the x value where the y value is 0. But the other key point is you find the x value where the y value is equal to 1, because that's a key point for logarithmic functions. Y-intercept, if it looks like this, it doesn't have a y-intercept, but there's some changes that can happen to this definition here of the function that could cause it to have a y-intercept. We'll see some examples about that. If it is increased, if b is greater than 1, if the base of the logarithm is greater than 1, the function is increasing. If the base of the logarithm is between 0 and 1, because you can have logarithm of 0.2 x, right? Then that function is going to be decreasing. As you can see in this graph here, that function will be decreasing. So the graph to the right shows how changing the base can affect the graph. As you can see, this is logarithm base 2. This is the natural logarithm, so it's basically the logarithm to the base 2.71 something. And this is the common logarithm, so it has a base of 10, logarithm to the base 10. Hope you can see that as the base of the logarithm goes up, because this is 2, this is 2.7, and this is 10, as the base goes up, the curve or the graph is kind of shrinking more and more. It's getting closer and closer to the x-axis. So that's what you can expect when the base of the logarithm is changing. So translations to these functions. We've talked about how this value c and this value d lead to changes or lead to transformations in graphs of polynomial functions, linear functions, exponential functions, and it's the same idea that we're following here. I hope you can imagine C shifts the graph horizontally. So the value of C, it can be plus or minus. If it's positive, it shifts the graph to the left. If it's negative, shifts the graph to the right. The value of D shifts the graph vertically. Again, if it's positive, it shifts it upwards, and if it's negative, it moves it downwards. A is usually the value before the function. If A is bigger than 1, the graph is stretched. Let me show you an example here. So if I have these are 3 graphs. Delete this, delete this. This is the logarithm of 2 x. And try to put another logarithm. Let me make it 5 of x. The graph of that is going to be that second red one. Why are they both red? Change that color to that, or green. Okay, so the green one is the 5, right? And what we're talking about is if a is greater than 1, the graph is stretched. If a is greater than 1, the graph is stretched vertically. So, and I think you can see how that stretch happens. If a is 5, the bigger the value of a, no, sorry, that is not a. Sorry. A value would be, so the a value here is 1. The a value in this equation is just 1. Right? So let me try to change the a value here to something like 2. It's the same base because it's the same logarithm, x. And I hope that shows it better, that the blue graph is stretched vertically by a factor of 2. What that means is initially where x was 2 and the y value was 1, this point has now been multiplied by 2 to become this new point here. And when x was 3 and, let me try to look for a distinct point. When x was 4 and the y value was 2, now this is going to be multiplied by 2. The y value is multiplied by 2, so the new y value is 4. And onwards and onwards and onwards. If a is between 0 and 1, the graph is compressed. I'll show you what that looks like. So if this is 1, because the y value is there is 1, but if I change this to a value like 0.5, then my graph now is compressed because this a value is between 0 and 1, so my graph is now compressed. It's getting closer to the axis, the x-axis. The general equation of all translations of logarithmic functions, and honestly of all other functions we've seen, is you have a logarithm x plus c. Remember, c shifts it to the left or to the right depending on whether this is a positive or negative. Base b, the b has to be, the b cannot be, as b changes, it leads to changes to the graph, which we saw earlier. The d, plus or minus d, if it is positive, it moves it up. If it's negative, it moves it down. Alright, so a is less than 0. If a is less than 0, that means if a is negative, if this number is negative, let's see what that does to the graph. If this number is negative, so if I make it a negative, what happens to my graph? Instead of being increasing, it is now decreasing. Same thing here, if it's negative, my graph is now decreasing. Let me just take out one of them. So my graph is decreasing instead of increasing. Yeah, so if a is less than 0, the graph is reflected over the x-axis. Yeah, we saw that on the graph. Reflected over the x-axis from being this to being that. reflected over the x-axis or decreasing. If the x is negative, if the x value is negative, if there's a negative in front of the x, then you expect that graph to be reflected over the y-axis. Let me show you what that means. If there's a negative in front of the x, the initial graph was this. But if there's a negative in front of the x, same graph, but instead of x, I'll do negative x, then that graph is reflected over the y-axis. Again, I don't know why this is not blue, green. Okay. So same graph, but it's reflected over the y-axis. And I hope you can see that this point, 1, 0, has now become negative 1, 0. Another point which would have been important is this point here. The key point, x is 2, y is 1, has now become x is negative 2, y is still 1, reflected over the y-axis. State the domain, range, and vertical. This is an example. The domain, range, and vertical asymptote of this, then sketch the graph. Now we know that because we cannot have logarithms of negative numbers, right? Hope you remember we cannot have a logarithm of negative 2 to any base, right? Because there is no power to which you can raise 10. There's no power to which you can raise any number, and then the answer turns out to be a negative number. So that's why we can't have logarithms of negative numbers. There's no possible value of x that you can put here, right? There's no possible value you can put there to come out with a negative number. So because of that, we know that whatever is inside the logarithm, or whatever comes after the logarithm in these parentheses, whatever is there has to be greater than 0, right? Has to be greater than 0. Can't even be equal to 0 because we also don't have a logarithm of 0. Same explanation. You cannot raise 10 to any power to get a 0, right? You cannot raise it to any power to get a 0. This number can't be raised to any power to give you a 0. So whatever is inside, whatever is after the logarithm has to be greater than 0. So this shows me that x has to be greater than negative 4. Since x has to be greater than negative 4, the value of x that would give me a 0 here is going to be my vertical asymptote, and that value of x is x equals negative 4. That's my vertical asymptote. Alright, so I know my vertical asymptote is x equals negative 4. Let me try to draw a line here. 1, 2, 3, 4. And remember, this has to be dotted because it's a vertical asymptote. That's my vertical asymptote, x equals negative 4. Now, I know that this x plus 4, that c value, because this is the c value we're talking about here, it means that the graph is moved or shifted 4 units to the left, right? That's why I already drew it here. The graph is shifted 4 units to the left. The parent graph of this function, is the graph of log of x to the base 3. The graph of log x to the base 3, remember the two key points that I need to look for is 1, x-intercept, and 2, the point where the y value is 1. So I need that x value for which the y value is 1, right? When I have those 2 points, I can draw my sketch nice and easy. So what do we have here? The question asks for domain, range, vertical asymptote. Okay, so if x is, let me first answer those questions and then go to these points and sketch. Since x has to be greater than negative 4, I know that my domain is going to be negative 4 to infinity. Okay, that's the domain finished. Range is always going to be negative infinity to infinity, unless there is crazy restrictions on the graph, in which case you deal with the question as it indicates. The vertical asymptote is here, right? So now I need to know what is the x-intercept. I know that the x-intercept is the value of x when y is equal to 0. So for this parent graph, because remember, I know that this parent graph was just shifted 4 units to the left. For this parent graph, what is its x-intercept? Its x-intercept is always going to be 1, 0, right? So its x-intercept was this point. but since it shifted 4 units to the left, I just count 1, 2, 3, 4. So that's where it is. The next point I look for is the point where the y value is 1, and I need that x value for which the y value is 1. So for this parent graph, log 3x, what value of x makes the y value equal to 1? Right? What value of x makes the y value equal to 1? To solve this equation, I'm asking myself, to what power do I raise 3 to get x? So I'm just going to do the reverse cycle. This goes to that, that goes to that. So this shows me that 3 to the power 1 is equal to x. So the x value is equal to 3, and the y value for that x value is 1. So that is for the parent graph. X value is 3, y value is 1. So that point was here, and I know that that point is also shifted 4 units to the left. So 1, 2, 3, 4. 4 units to the left. When I have those 2 points, I am safe to sketch the graph because I know it has a nature of, it's asymptotic at this point. Just sketch it as, oops, missed the point. Asymptotic. Yeah. Sketch. Actually, it looks more curvy than straight, because mine looks more straight than curvy. But yeah, so that's what it is. If you really want, if you're interested, you can also find this y-intercept, but that's hard to do without a calculator, and this is the kind of question you'll be asked to solve without a calculator. So yeah, but it's possible to find the y-intercept. It's simply the y value when x is 0, and you can try to solve for that from this equation and see what it gives you. Alright, looking at the next example, state the domain, range, vertical asymptote of this function. Now this function, I can see that there's a negative before the x, and I hope you remember that a negative before the x, if the x is negative, what does that mean? It means the graph is reflected over the y-axis, right? So I expect my graph, instead of looking like this, I expect my graph to look like that. Just putting that up there before we start. So domain, range, vertical asymptote. I know that anything, whatever is inside the logarithm has to be greater than 0 for the domain. So whatever is inside the logarithm, 12 minus 3x, has to be greater than 0. Cannot be equal to 0, has to be greater than 0. This means if you solve is 12 is greater than 3x, I'm taking the negative to the other side. 12 is greater than 3x. So if I divide by 3 both sides, I'll have x is less than 4. If you follow that slowly, because this goes to 4 is greater than x, which means x is less than 4. So my domain is going to be negative infinity to 4, because x is less than 4. And that means that my vertical asymptote is going to be x is equal to 4. That's my vertical asymptote. Alright, so the next thing I need to do is to sketch the graph. Now, my advice, and you can, it's possible to do it differently, but my advice is to first ignore this part, because this d value simply tells you that the graph is shifted 4 units down. Right? The graph is shifted 4 units down. Let's focus on this equation, this logarithmic equation, and then see how that is changed. See how that is changed, and then go ahead to just move whatever you get 3 units down. So that's what I'm going to do. I know that the 2 key points that I need are 1, x-intercept, and the key point, because the x-intercept is when the y value is 0. I don't know the x value, but I'm going to try to find that x value. And the other key point is the value of x, let's call it b, that makes the y value equal to 1. So starting with the x-intercept, I know the y value is equal to 0, so I'm looking for what makes this function, this part of the function, log 2 12 minus 3x, what makes that equal to 0? 12 minus 3x, I want that to be equal to 0. If that is equal to 0, then using this idea, I'll have 2 to the power 0 is equal to 12 minus 3x. 2 to the power 0 is the same thing as 1. 12 minus 3x. If I simplify this, I have 3x is equal to 11, so x equals 11 out of 3. So that point is x is 11 out of 3 and 0. And 11 out of 3 is the same thing as, calculator, I think it is 3.3. 11 divided by 3. No, 3.7. So that's 3.7 and 0. That's my x-intercept. The other point I'm looking for is the key point, where the y value is equal to 1. So I want, let me write it here, I want the logarithm of 12 minus 3x base 2 to be equal to 1. So if I do the cycle, I'll have 2 to the power 1 is equal to 12 minus 3x. And then simplifying this, I have 3x is equal to 10. So x is equal to 10 divided by 3. 10 divided by 3, that should be 3.3. And the y value is 1. So I have 2 points. I have 2 points. X is 3.3 and 1, and then the other point is 3.7 and 0. So that's the x-intercept is 3. Before I start drawing, let me first draw my vertical asymptote. X is equal to 4, 1, 2, 3, 4. Vertical asymptote goes in there. Oops. Vertical asymptote. Okay. Then I start putting in the points that I have. One is 3.70. That's my x-intercept. 3.7. This is 3. 3.7 is somewhere here. But remember that this point is going to be moved 3 units down. So this point 3.7 somewhere there and 0. It's moving 3 units down. So 1, 2, 3. And then the next point is 3.3 and 1. X is 3.3 somewhere here, and y is 1. That's that point. That point is moving 3 units down as well. So 1, 2, 3. So that's what I have. And with those 2 points, I'm able to sketch the graph of this function. On your sketch, these are the 2 points that should be appearing very distinctly, right? And it happens that they're very close in this one, but that's not a big deal. Is it possible to figure out the x-axis for this graph? Yes, it is very possible. But will it require calculation? I'll try to find the x-axis afterwards, after sketching this. So I have my 2 key points, and then I'm going to sketch my graph looking like this. Oops. X, that's my graph looking very shabby, but yeah, you get the idea. So let me try to find the x-axis just for those who are curious. I mean the x-intercept. So I know that the x-intercept is the value where this whole function equals 0. So I'm going to include this part in the function because I'm trying to find the x-intercept of that whole function. So log 2, 12 minus 3x minus 3, all of that must equal 0. So that means log 2, 12 minus 3x must equal 3. So if I simplify, 2 to the power 3 is going to equal that. 2 to the power 3 is equal 12 minus 3x. So I have 3x equals 12 minus 8, which is 4. And then x is equal to 4/3, which 4/3 is 1.3 and 0. So that x-intercept is 1 point, which is actually very close to what I drew. Because if this is 1, 1.3 should surely be somewhere there, and 0. So I have my point, 1.3 and 0 as my x-intercept. Like I said, the 2 key points that you need to be finding are these ones, right? But if you go ahead and find the x-intercept, no biggie. The y-intercept is also possible to be found if you're interested, but you might need to use a calculator, and if the question had asked you to not use a calculator, that would be a restriction. But again, if you're interested, I'll show you here, hope you can fit. The y-intercept is the value of y when the x-intercept is 0. So I'm just looking for y when I substitute for log 2, 12 minus 3x, so 12 minus 0, subtract 3. There's no way I can figure this out without using a calculator, because 2 doesn't have a direct, 12 cannot be expressed in terms of powers of 2. So this simplifies to log 2, 12, subtract 3 to get the y value, and I will need to put this in a calculator to get that y value. So let me try to put it in a calculator here. Scientific. So on these calculators, when I do logarithm of what's happening? 12 logarithm. Okay. I'm going to divide that by the logarithm of 2, because on these calculators log is already programmed to be a common logarithm to the base 10. And that gives me 3.58, and then when I subtract 3, then I get 0.58. So on this, my graph was supposed to have cut somewhere here, but again, since it's just a sketch, these are the only 2 points that you need to draw your sketch. This and this come in as extras. If the question had asked you to not use a calculator, there's surely no way you could have done the y-intercept. This question didn't specifically ask us for the x-intercept, so we didn't have to do this. It just helps you for your sketch to look closer to the accurate thing, but in terms of answering what this question asked, it's these 2 points, the vertical asymptote and the domain. Didn't even ask for range. Oh, range, sorry. Range is negative infinity to infinity. Alright, last one. We're trying to write an equation for this graph. And they've told us that the parent graph is log of 3 to the base x. Now, I already can see, because I expect the logarithm of 3 to the base x, of x to the base 3, I expect that logarithm to look like this. I expect the graph to look like that, right? To be increasing. But since it's not increasing, it is decreasing, I know something happened. And I can look back here to see what can cause that to happen, right? This a value, if that a value is less than 0, the graph is reflected over the x-axis, right? Reflected over the x-axis. What does that mean? Does this look like it's reflected over the x-axis? Let's go here and see. To the graph. So remember, if I were to change this base to 3, and then if I were to change that base to 3, then that's the red graph. And then if I put a negative here, and still change this one to 3, then that's what I see, right? If I changed, the red graph is just log 3 to the base x. If I change this to be a negative, then I have the green graph, which looks like it is decreasing instead of increasing, and it also looks like it's reflected over the x-axis. But that's not all that's happening to my graph. On top of having that happen to it, my graph is shifted a couple of units to the left. So let me see, 1, 2, 3, 4. So this x is shifted 4 units to the left, and that's represented with a +4, right? 4 units to the left. So I am expecting my function to be something like this: negative a logarithm of 3 x plus 4, right? The 4 is because it's shifted 4 units to the left. That's visible. 1, 2, 3, 4. Now I need to figure out what this a value is. In order to figure out this a value, I'm going to find one of the points on the graph and then just substitute for the x and y values of that point. So I need to look for a distinct point, like a point that passes through an intersection of, a square like this, like at that point. So this is one of them, alright, but there's another one here. This one is x is negative 1 and y is negative 3. X is negative 1, y is negative 3. Alright, so using the output value as negative 3 equals negative a logarithm x plus 4, x is negative 1 plus 4 to the base 3. I can use this to figure out what the value of a is. So negative 3 is equal to negative a logarithm of the base 3 to power 3. I know logarithm of 3 base 3 is 1 because logarithm means what power do you raise 3 to get 3, and that power is 1. So this logarithm is just 1. So I end up having that negative 3 is equal to negative a. So my a value is 3. So my logarithm equation, this one, f of x, is equal to negative a logarithm of x plus 4 to the base 3 is simply going to be, since I found what a is 3, it's just going to be negative 3 logarithm x plus 4 to the base 3. And I can check my answer by I put a negative 3 here and put a plus 4. The graph is the same graph that I have in that question. This point is negative 3 1, negative 1 3, sorry. This point is negative 3 0. So yeah, that's how you do a question like that. Now, if I had used the positive a here, because that might be better. If I'd used the positive for a, then this would be positive, this would be positive, this would be positive, and then my a value would be negative 3, which I would still just substitute back here as a negative 3. So I hope that didn't just confuse you 5 times over, but yeah, it's the same thing. Alright, this is your homework. I hope you can enjoy the homework.